All right, hello. My name is Christopher Murzadeh. This is the final project for Thermodynamics of Mechanical Systems with Professor Yoav Peles. My major is mechanical engineering, and I was responsible for creating the schematic of the system that we were analyzing, the state table, and I did the EES code and the associated parametric evaluations. And I spent approximately 25 hours on this project.
My name is Tyler Gould. I'm also a mechanical engineer, and my duties for this project were to help come up with the idea for the system. I helped with the TS diagram as well as did the first law analysis. And all of that took me roughly 12 to 15 hours total.
All right. Hi, I'm Christian Farley. I am also a major for mechanical engineering. I was tasked with the exergy analysis for our system, and in total, I spent around, let's say, 10 to 12 hours on this project. All right, so here's a schematic for our process that we came up with. Essentially, we came up with a refrigeration cycle that's going to have our two evaporators within it. This system will be using refrigerant 134A as its working fluid. Within the system, as you can see, we also have the two heat exchangers to transfer heat for the saturated vapor coming out of those evaporators. We've decided that the compressor is going to operate as non-ideal and operate at a 60% efficiency. And by having these two evaporator branches, this will allow the fluid to operate at two different temperatures at the same time, which would be beneficial since in our example, we are having one evaporator operate a refrigerator, whereas the other one would have to operate a freezer at that lower temperature. So for this schematic, we did decide that the operating pressure for that condenser is going to operate at 1 megapascal, and obviously that refrigerant leaving the condenser would be a saturated liquid. The refrigerant that enters the freezer evaporator, that's going to operate at 100 kilopascals, whereas the refrigerant that enters that refrigerator evaporator, that's going to be operating at 250 kilopascals. Now, the refrigerant will be exiting both evaporators as a saturated vapor. And then, as mentioned beforehand, sent through those heat exchangers. And for the refrigerator refrigerant, that will be sent through that pressure reducing valve before it meets back up with the refrigerant that came out of the freezer evaporator. And then they'll combine into one line again and restart the cycle before entering that compressor.
And what you see here is the TS diagram that basically displays everything that Christian just laid out for our system. So you'll see on the right is state one, which is where it enters the compressor, increases its pressure up all the way up to the highest isobar, and then it comes down and through state 2 to 3, it's going through the condenser, and then at from state 3 to 4 and 8, you'll see it actually diverges. That's where our flow is diverging to the two separate pressures, and it's dropping down to state 5 and 9 on the two different isobars, and then across this to the saturation line where it exits each evaporator as a saturated liquid, as Christian said. And then those go down, and you can see at state 12 is where both of the flows meet back together again, and it becomes a whole single mass flow. back into state 1, which is where it gets pumped back into the compressor.
All right, now what we have here is the state table. Um, Basically, this is a table that's filled with all of the values, the properties at each of the states that we just described. These values were calculated through EES, and they were all established, or they were all calculated based on these established values here with the condenser pressure of 1000 kPa, evaporator at 100, evaporator 1 at 100 kPa, evaporator 2 at 250 kPa, and the compressor efficiency at 0.6. We also had to establish the cooling load of the first evaporator to be 4 kilowatts. The other value that we established here was that the mass flow rate going into one of the condensers was going to be half of the mass flow rate going into the other condenser. And then we needed to establish these values just to make sure that the rest of the values could be calculated.
On this screen, what you'll see is our first law analysis, where we broke down each individual component that has either a mass transfer, heat transfer, or some sort of work going through it, considered it as a control volume so that we could apply the first law of thermodynamics to it and then figure out what the work for each component, or well, really work for the compressor and then the heat transfer between each of the condenser and then the respective evaporators. The heat exchanger analysis also shows that each fluid path on each side, which is they are not an open heat exchanger, they're closed, so they're separate flows, but it shows that the enthalpy change between both of them is equal, which is ideal, and that's how it is able to increase the efficiency for the system. And we also have on the right, which is actually the first law or one of the laws of mass conservation. And it shows basically where our mass separates and becomes two separate masses, and how we've divided the amount of the flow. And then below that is where it goes back together and how you can represent them mathematically with y, and then 1 minus y, which represents the portion of each. And at the very bottom, we noted how we divvied up the mass by default, which was that one flow was inevitably twice the mass of the other one. And you can see that at the very bottom because it's 2 m.8 plus m.8. And that sums up the work and heat and mass transfer in the system.
All right, so here I'll be diving into the exergy analysis. So some important temperatures that needed to be set in order to calculate our exergy would be our TO set at 25 degrees Celsius. That is going to represent the temperature, essentially like room temperature that this system would be placed within. TH, which will be relating to the condenser, which is set at 30 degrees Celsius. TL1, which is going to correspond to the evaporator that goes to the refrigerator, is set at 3 degrees, whereas TL2, which is the evaporator for the freezer, which we set at negative 18 degrees. So essentially, for exergy, we need to understand the exergy going in and the exergy going out for each of the components. So diving in at our evaporator number 1, here we have exergy entering the system in a form of heat, and that formula is as stated there, where our Q dot L1 is going to be multiplied by 1 over TO over TL1. Our compressor has exergy entering that in a form of work. And that equation is as follows, because exergy entering in a form of work is going to be equal to the work on that component. Looking at our condenser, The equation is very similar to that evaporator, except the exergy will be leaving the system in a form of heat. So again, very similar equation, except those QL and TLs will be replaced with QH and TH. And then evaporator 2, same thing with our evaporator 1. We're just changing out that Q dot L value for the Q dot L2. Same thing with the TL1 to the TL2. So when we look at the heat exchanger, expansion valve, and pressure reducing valve components of our system, because there's no heat transfer occurring going inside these components or outside the components in relation to the actual system, as well as no work being done on these components, we can infer that there's no exergy going in or out at these points as well. So again, once we have those exergy in and exergy out values, we can use that to calculate the total exergy destroyed, which I will show you on this next slide. So here we essentially quantify the exergy analysis. These are going to be the same equations I just described on the last slide. These values are going to be what we found for our QL1, our QL2, and our QH, which we'll go over during one of the later slides. But here we can see in total, we have our QN, which is going to be about 5.37 kilojoules, our Q out, which is going to be that 0.28 kilojoules, which will give us our total destroyed exergy at 5.093 kilojoules, which makes sense because this isn't a perfect, completely optimal system. So we're obviously going to have some exergy destroyed here.
All right, so now we're going to look at some of the parametric evaluations that were done upon the system. So this evaluation is the compressor work versus the compressor efficiency. This looked at how the variation in the compressor efficiency affected the amount of work that was required to operate the compressor. As we can see here, the compressor efficiency increases the amount of work that is required to operate the system. As the compressor efficiency increases, the amount of work required to operate the system goes down. And this makes sense because the more efficient the compressor is, the less work input will be required to compress the refrigerant. And all in all, it's pretty obvious that like in order to identify the optimal operating conditions, it would be to have the most efficient compressor as possible. And these here are the values that were run. The next parametric evaluation that we looked at was looking at the COP versus the compressor efficiency. As would be expected, the performance of the system increases as the efficiency of the compressor goes up. This is just another data point that establishes the fact that a more efficient compressor will yield a more optimal operating condition. And then the next here, basically we analyzed the COP with respect to how much mass flow rate was going from state 3 into the first evaporator as compared to the second evaporator. It can be seen here from the figure that the less mass flow rate going into the first evaporator yields greater levels of performance. This is likely due to the fact that we established a fixed value for the pressure and the cooling load for evaporator 1. So if less flow rate was provided to the evaporator, more would be going into the evaporator 2, causing the variable cooling load of evaporator 2 to be higher. But it should be noted that the difference in between having one in the spectrum from having a higher mass flow rate to a lower mass flow rate is very, very small. There's not a terrible amount of difference. Here we have just a copy paste of the code. I'm actually going to go into the code a little bit more and run it to show how we looked at it in EES here in a second. But basically, this code was created systematically by starting from the established values and then using knowledge and assumptions that were made that are known to be true of refrigeration systems, and to find the other values. Uh, so one example here is that we use the pressures that were established and plus the knowledge of the quality of the states out of the condenser and the evaporators to ID all of the other properties at states 3, 6, and 10. Also, we used the established value of the compressor efficiency to find H2 with this equation here. Also, we use some of the first law equations to find the enthalpies for some of the other states that surround the heat exchangers. And then once we found all of those, and we had two intensive independent values for each of the states, we were able to fill in all the gaps and fill out that state table that we showed on the previous slide. These are the results that come from the EES, and I'm going to quickly show the EES and run the code just to show how it goes. So this is our code here. And then once we run it here, we had 98 equations, and then we can just look at the results. And this shows all the results from the temperature all the way to the exergy values. And that is the end. Thank you very much.